Imagine waking up one morning and seeing a faint glow covering everything around you, a light so ancient it's been traveling across the cosmos for over 13 billion years. That's the cosmic microwave background, or CMB, the universe's oldest baby picture, a snapshot of what everything looked like when it was just 380,000 years old. This isn't just some distant cosmic curiosity, it's the afterglow of the Big Bang itself, the faint echo of creation that surrounds us all, filling every corner of space like an invisible whisper from the dawn of time. What's even more mind-blowing, that glow isn't just a relic, it's a treasure chest of secrets. Hidden within its subtle ripples and temperature variations are clues that rewrite our understanding of everything. The birth of galaxies, the fate of the universe, even the existence of dimensions we can't see. Scientists call it the most important discovery in cosmology since we realized the Earth wasn't the center of the universe. And yet, most people have no idea just how bizarre, how profound, or how downright mysterious the CMB really is. That's where this journey begins. Over the next 30 revelations, we're diving deep into the cosmic detective story behind this primordial light. From the accidental discovery that stunned astronomers to the eerie anomalies that still keep them up at night, you'll uncover why the CMB is more than just ancient radiation. It's a time machine, a cosmic blueprint, and maybe even a doorway to realities beyond our own. So if you've ever looked up at the night sky and wondered how it all began, hold on tight. The universe is about to spill its oldest secrets. Here's something wild to wrap your head around. No matter where you are in the universe, even in the deepest, emptiest void between galaxies, you're swimming in the cosmic microwave background. It's not just somewhere out there, it's literally everywhere, a ghostly hum of microwave radiation left over from the Big Bang, saturating every cubic inch of space. Think of it like an invisible ocean, one that doesn't just surround you but passes right through you, unchanged and unending, no matter where you go. And here's the kicker. It's almost perfectly uniform, like a vast, smooth sheet with only the tiniest ripples. Point a radio telescope in any direction, and you'll pick up the same faint signal, just a few degrees above absolute zero. That uniformity is one of the most jaw-dropping clues we have about the early universe. It tells us that back when the cosmos was just a seething plasma of particles and energy, everything was incredibly smooth, almost eerily so. How could something so vast be so evenly spread out? That mystery alone led scientists to some of the most radical ideas in physics, like cosmic inflation, the theory that the universe expanded faster than light in its first fraction of a second, ironing out all the wrinkles. But don't let that smoothness fool you. Those tiny variations in the CMB, barely a whisper of difference from one spot to another, are the universe's most important fingerprints. They're the seeds of everything: galaxies, stars, even us. Without those faint fluctuations, gravity wouldn't have had anything to cling to, and the cosmos would have stayed a featureless soup forever. So next time you look up at the night sky, remember, you're not just seeing stars, you're seeing the echoes of those primordial ripples, the blueprint of existence itself, written in microwaves. The cosmic microwave background holds a cosmic record that might surprise you. It's officially the coldest natural thing in the entire universe. Clocking in at just 2.7 Kelvin, that's a mind-numbing negative 270.45 degrees Celsius, colder than the darkest voids between galaxies, colder than the surface of Pluto, even colder than the Boomerang Nebula, previously thought to be the chilliest spot in space. That temperature isn't just a random number, it's a direct message from the infant universe, a relic of a time when everything was cooling from the unimaginable heat of the Big Bang. Think about this for a second. Space itself isn't empty. It's teeming with energy, starlight, and radiation from countless sources. Yet the CMB cuts through it all like an icy whisper, so cold that it defies even the most extreme environments we've discovered. Distant galaxies, their heat outshines it. The vast cosmic voids, they're still warmer by comparison. Even the frigid expanse of intergalactic space, where temperatures plummet to just a few degrees above absolute zero, can't compete. The CMB is the ultimate baseline, the universe's natural freezer, chilling everything to its faint, persistent hum. This unbelievable coldness isn't just a curiosity, it's proof of how far the cosmos has come. When the CMB first formed, the universe was a scorching plasma, thousands of degrees hot. But as space expanded, stretching that primordial light into longer, weaker wavelengths, its energy diluted into the feeble microwave signal we detect today. That relentless cooling tells the story of cosmic inflation, the relentless stretching of space-time itself. And here's the wildest part, that temperature isn't just cold, it's perfectly tuned. If the CMB were even slightly warmer, atoms might never have formed. Slightly colder, and the seeds of galaxies wouldn't have clumped together. This isn't just a relic, it's a fingerprint of the universe's delicate balance, the Goldilocks zone of existence itself. So next time you feel a winter chill, remember somewhere out there, the ghost of the Big Bang is colder than anything nature has ever created. A silent witness to the universe's fiery birth and its long, slow journey into the cold. Here's a remarkable twist in the cosmic microwave background story. It wasn't discovered by accident. Well, technically it was stumbled upon, but here's the kicker. Brilliant minds had already predicted its existence 2 decades earlier. Back in the 1940s, long before any telescope could detect it, a trio of visionary physicists George Gamow, Ralph Alpher, and Robert Herman were piecing together the aftermath of the Big Bang and realized something astonishing. If the universe began as a searing hot explosion, they reasoned, it must have left behind a fading glow, a cosmic fingerprint cooling over billions of years. Gamow, a playful genius who once added a fictional co-author to a paper just to make the list read, Alpha, Beth, Gamow, led the charge. He and his colleagues calculated that the radiation from the Big Bang wouldn't just vanish, it would stretch into microwaves as the universe expanded, settling into a faint but detectable background hum. Their math even nailed the temperature, around 5 Kelvin, strikingly close to the actual 2.7 Kelvin we measure today. But here's where it gets bittersweet. At the time, the technology to test their theory didn't exist. Radio astronomy was in its infancy, and the idea of hunting for an omnipresent cosmic signal seemed almost like science fiction. Fast forward to 1965, and 2 radio astronomers, Penzias and Robert Wilson, were wrestling with a persistent hiss in their antenna at Bell Labs. No matter where they pointed it, the noise wouldn't go away. They scrubbed off pigeon droppings, checked for electrical interference, even dismantled and reassembled their equipment. That annoying hum, it was the CMB, the very relic Gamow's team had foreseen. The irony, Penzias and Wilson weren't even looking for it. They'd tripped over the most important cosmological discovery of the century while trying to eliminate what they thought was faulty equipment. When Gamow heard the news, he reportedly laughed and said, "Well, I told you so." But the real punchline, the Nobel Prize went to Penzias and Wilson, not the theorists who'd paved the way. It's a reminder of how science often unfolds brilliant ideas whispering in the dark, waiting for technology to catch up. And it begs the question, what other cosmic secrets are lurking in plain sight, predicted but still just out of reach? The story of how the cosmic microwave background was discovered reads like a cosmic comedy of errors, one where the punchline just happened to rewrite the history of the universe. Picture this, 2 determined radio astronomers, Penzias and Robert Wilson, perched on a hill in Holmdel, New Jersey, in 1965, armed with a massive horn-shaped antenna originally built for satellite communications. Their mission, to measure radio waves from distant celestial objects, but there was a problem. A maddening, unexplained hiss plagued their readings. No matter where they pointed their antenna, day or night, this persistent static refused to disappear. At first, they blamed the pigeons. Yes, pigeons. A colony of the birds had taken up residence in the antenna's reflector, leaving behind what Penzias delicately called a white dielectric material. The duo scrubbed the equipment clean, even evicting the birds and their messy contributions, but the noise stubbornly remained. They checked every conceivable source of interference, nearby radio stations, military radar, even the vibrations from nearby New York City. Nothing worked. The universe, it seemed, was whispering a secret they couldn't yet decipher. Meanwhile, just 30 miles away at Princeton University, a team led by physicist Robert Dicke was actively hunting for the CMB. They'd built their own detector, expecting to find the faint afterglow of the Big Bang, when Penzias and Wilson, frustrated and baffled, reached out for advice. Dicke's reaction was legendary. After hanging up the phone, he reportedly turned to his colleagues and said, "Well, boys, we've been scooped. The static wasn't interference, it was the echo of creation itself, the very signal Dicke's team had hoped to find." The irony, Penzias and Wilson weren't even looking for the CMB. They'd tripped over the most important cosmological discovery of the century while troubleshooting what they thought was faulty equipment. When they published their findings, the scientific world erupted. Their nuisance signal matched the exact frequency predicted by Big Bang theorists, confirming the universe had a definitive beginning. And in 1978, their accidental discovery earned them the Nobel Prize in Physics. But here's the real kicker: this wasn't just a stroke of luck. Their meticulous efforts to rule out every possible error showcased something profound. Sometimes the greatest discoveries aren't found by those seeking them, but by those patient enough to listen when the universe refuses to be ignored. And that static, it's still there today, humming softly in every corner of the cosmos, a reminder that even our best science begins with a simple question: what is that noise? Think of the cosmic microwave background as the universe's very first baby picture, one taken just 380,000 years after the Big Bang. At that exact moment, something extraordinary happened. The cosmos finally became transparent. Before this, the universe was a seething, opaque fog of plasma, so dense with free electrons that light couldn't travel more than a hair's breadth before scattering. But as everything expanded and cooled, electrons and protons finally slowed down enough to combine into hydrogen atoms, the simplest building blocks of matter. Suddenly, like fog lifting, light broke free. This moment, called recombination, is frozen in time within the CMB. The photons released then have been traveling ever since, stretched by the expansion of space into the microwaves we detect today. What we're seeing isn't just ancient light. It's the last gasp of the universe's fiery infancy, the instant transition from a chaotic plasma to a place where structure could begin to form. Here's the staggering part: when we map the CMB, we're not just looking at a distant object. We're seeing the boundaries of the observable universe itself, the farthest back in time we can possibly peer. Those faint temperature variations, their density fluctuations, slightly hotter spots where matter was more crowded, cooler regions where it was thinner. Over billions of years, gravity amplified these tiny differences into the galaxies and voids we see today. It's as if the universe handed us a blueprint showing exactly where stars would ignite and cosmic structures would take shape. Yet this baby picture holds mysteries too. Why is the CMB so remarkably uniform across vast distances? How did regions too far apart to ever interact somehow reach the same temperature? These questions led to the theory of cosmic inflation, a faster-than-light expansion in the universe's first fraction of a second, smoothing everything out before recombination. The CMB doesn't just show us the past, it's forcing us to rewrite the story of how everything began. So next time you glance at a baby photo, remember, the universe has one too, and it's the most revealing selfie ever taken. At first glance, the cosmic microwave background appears almost boringly smooth, a uniform sea of microwaves bathing the universe. But look closer and you'll find something extraordinary. microscopic temperature variations no more than 1 part in 100,000, scattered like cosmic confetti across the sky. These faint fluctuations, called anisotropies, are anything but random. They're the universe's genetic code, imprinted at the moment of recombination, and they hold the secret to why the cosmos looks the way it does today. Each tiny hot spot or cold spot in the CMB represents a region where matter was slightly denser or sparser in the early universe. Over billions of years, gravity amplified these differences like a cosmic snowball effect where denser regions pulled in more material, eventually collapsing into galaxies and galaxy clusters. The cooler patches, they became the vast, empty voids between them. What's astonishing is the scale of this transformation. Those imperceptibly small variations, some just a few millionths of a degree, grew into the jaw-dropping structures we see today, from the delicate filaments of the cosmic web to the towering walls of galaxy superclusters stretching across billions of light years. But here's where it gets even stranger. The pattern of these fluctuations isn't just a map of matter we can see, it's a ghostly imprint of dark matter's invisible grip. When scientists compare the CMB's anisotropies with the distribution of galaxies today, they find a discrepancy. The seeds in the ancient light are too pronounced to be explained by ordinary matter alone. The only way the math works, an unseen, mysterious substance, dark matter, must have been there from the start, sculpting the universe's structure long before stars or planets existed. The CMB doesn't just show us the past, it's proof that most of the cosmos is made of something we still don't understand, and then there's the spacing. The anisotropies aren't scattered randomly, they follow a precise pattern of peaks and valleys in what scientists call the power spectrum. The first peak reveals the universe is geometrically flat, a critical clue about its total energy content. The second and third peaks, they're like cosmic fingerprints encoding the proportions of ordinary matter, and dark energy. It's as if the universe left us a carefully tuned radio signal, and by adjusting the dial, we can decode its deepest secrets, from the amount of hydrogen in existence to the fate of everything billions of years from now. Perhaps most mind-bending of all, these fluctuations were set in motion by quantum mechanics. In the first fraction of a second after the Big Bang, microscopic quantum ripples were stretched to cosmic scales by inflation, becoming the density variations we now see in the CMB. That means the largest structures in existence, galaxy clusters, supervoids, even the entire cosmic web, owe their existence to subatomic randomness magnified to unimaginable proportions. The universe's grand design, it turns out, was written in the smallest possible handwriting. So the next time you hear static on an old radio, think about this. Buried in that noise might just be the faint echo of quantum fluctuations from before time began, now frozen in the sky as the blueprint for everything. The CMB isn't just a relic, it's the universe's original instruction manual, and we're only just learning how to read it. Before the cosmic microwave background was discovered, the universe's origin was up for debate. Some scientists champion the steady-state model, a universe with no beginning or end, continuously creating new matter to maintain its density as it expanded. It was elegant, eternal, and completely wrong. The CMB didn't just support the Big Bang theory, it obliterated every competing idea with the quiet authority of a whisper louder than a supernova. Here's why the CMB is the smoking gun of cosmic origins. According to the Big Bang, the early universe was a roiling soup of particles and energy so dense that light couldn't escape. As it expanded and cooled, that trapped radiation finally broke free, creating a glow that would stretch into microwaves over billions of years. The steady-state model, by contrast, predicted no such background radiation. There was no primordial fireball in its version of events, just an endless, unchanging cosmos. When Penzias and Wilson detected that uniform microwave hum in 1965, it wasn't just a discovery. It was a verdict. The CMB matched the Big Bang's predictions with uncanny precision. while leaving steady-state theorists scrambling to explain why their universe had a ghostly afterglow it shouldn't possess. But the CMB didn't stop there. It handed scientists a second gift, the spectrum of its light. When you analyze the CMB's energy distribution, it follows what's called a blackbody curve, a perfect thermal fingerprint of an object's temperature. And this wasn't just any blackbody curve. It was the most flawless one ever measured in nature, a match so exact it looked like a textbook diagram. That perfection was another knockout punch for the Big Bang. Only an intensely hot, dense early universe, one that had cooled through expansion, could produce such a pristine signal. Steady-state models couldn't replicate it. Even alternative theories like the tired light hypothesis, which suggested light loses energy over vast distances, failed to explain the CMB's specific temperature and uniformity. Then came the clincher, the CMB's tiny fluctuations. The Big Bang model predicted that quantum ripples in the infant universe would leave faint imprints in the radiation, variations that would later grow into galaxies. When satellites like COBE and Planck mapped the CMB in exquisite detail, that's exactly what they found, a cosmic ledger of density variations penned in microwaves. No other theory could account for this intricate pattern. The steady-state universe, with its eternal sameness, had no mechanism to create such structured imperfections. The CMB wasn't just evidence, it was a time-stamped document signed by the universe itself, proving it had a fiery beginning. Yet the most poetic part isn't just that the CMB confirms the Big Bang, it's how it does so with humility. This ancient light doesn't shout, it doesn't blaze across the sky. It's a whisper from the edge of time, so faint that detecting it required instruments of extraordinary sensitivity. And in that whisper lies the universe's greatest confession. It had a birth, a moment when everything, time, space, matter exploded into being. The CMB doesn't just prove the Big Bang, it's the universe's own memory of its first breath, a story written in microwaves for anyone patient enough to listen. The cosmic microwave background isn't just ancient, it's fading. Like an old photograph left in the sun, its signal is slowly dissolving into the void as the universe stretches ever outward. Every second as space expands, those primordial microwaves lose a little more energy, their wavelengths elongated into weaker, cooler signals. It's a silent retreat, one that raises a startling question. If we'd been born billions of years earlier, would the CMB have been too bright to ignore, blazing across the sky like a second sun? And if we wait long enough, could it vanish entirely? This gradual dimming isn't just a cosmic curiosity, it's a direct consequence of the universe's expansion. When the CMB first broke free, its photons were packed with energy, radiating at temperatures around 3000 Kelvin, glowing like the surface of a star. But over 13.8 billion years, the stretching of space has redshifted that light, stretching its wavelengths 1,000-fold into the microwave range. Today, it hovers just above absolute zero, and the process isn't stopping. As the cosmos continues to expand at an accelerating rate, the CMB's temperature will keep dropping, its signal growing fainter with each passing eon. Here's where it gets even more mind-bending. Right now, the CMB is detectable because its wavelengths fall within the microwave band, a sweet spot for our telescopes. But in about 150 billion years, models suggest the expansion of space will stretch those microwaves into radio waves so long and feeble they'll blend into the background noise of the universe. By then, the CMB's temperature could plummet to a barely measurable fraction of a degree above absolute zero. For civilizations emerging in that distant era, the afterglow of the Big Bang might be utterly invisible, lost in the vast silence of an older, colder cosmos. They'd have no easy way to confirm the universe had a beginning at all. This cosmic erasure carries profound implications. The CMB isn't just a relic, it's a time-sensitive message, one that future astronomers might never stumble upon. Without it, piecing together the universe's origin story would be like reconstructing a fire from its ashes long after the flames have died. The very evidence that transformed cosmology in the 20th century could become inaccessible, leaving distant descendants to wonder if the cosmos had always been this quiet, this dark. Yet, even as the CMB fades, it leaves behind a final lesson. Its slow disappearance mirrors the fate of everything in an accelerating universe. Galaxies beyond our local group will eventually redshift out of view, their light stretched beyond detection. The night sky, now teeming with distant stars, will one day appear empty to far future observers. The CMB's quiet farewell is a preview of cosmic isolation, a reminder that the universe's most important stories aren't just written in light, they're written in time, and some chapters are only visible for a while. So while we still can, we listen. Every measurement, every map of the CMB is a snapshot of a signal that won't last forever. It's the universe's oldest broadcast, and one day its transmission will end. But for now, the afterglow remains a flickering candle in the dark, holding secrets we're only beginning to understand. That near-perfect smoothness of the cosmic microwave background. It's an illusion. Peer closer, and you'll find the universe's surface is etched with incredibly subtle wrinkles, temperature variations so tiny they'd make a single grain of sand on an entire beach seem obvious by comparison. These minute fluctuations, just one part in 100,000, are anything but cosmic static. They're the universe's birthmarks, fingerprints left behind from a time when everything was a seething, uneven plasma, and they hold the key to understanding why the cosmos looks the way it does. Take the hottest and coldest spots in the CMB maps, a region slightly warmer than average, say by a few millionths of a degree, was once a slightly denser pocket of the early universe. Over billions of years, gravity amplified those microscopic overdensities, pulling in surrounding matter until they snowballed into the galaxies and galaxy clusters we see today. The cooler patches, they became the vast cosmic voids, the empty stretches between the glittering structures. What's staggering is the scale of this transformation. Those barely their ripples, imprinted when the universe was a toddler, grew into the web of superclusters and filaments that span billions of light years today. This is how the universe builds itself, starting with quantum whispers, ending with celestial skyscrapers. But here's the twist: without those imperfections, the cosmos would be a featureless wasteland. A perfectly smooth CMB would mean no density variations, no gravitational footholds for matter to clump together. Stars would never ignite, planets wouldn't coalesce. Life as we know it would be impossible. Those tiny temperature differences aren't just curiosities, they're the universe's way of breaking its own symmetry, introducing just enough chaos to spark creation. It's as if the cosmos knew it had to leave behind these breadcrumbs, these microscopic departures from uniformity, to give rise to everything that followed. Dive deeper and the plot thickens. The pattern of these fluctuations isn't random. It follows a precise mathematical rhythm called the power spectrum. Imagine the CMB as a musical chord with certain notes resonating louder than others. The first peak in this cosmic symphony tells us the universe is geometrically flat, a critical clue about the total energy density of space. The second and third peaks reveal the ratio of ordinary matter to dark matter, like a recipe written in microwaves. When scientists analyze these peaks, they're effectively reading the universe's DNA, decoding the exact proportions of its ingredients from a time long before atoms existed. Perhaps most mind-bending of all is what seeded these variations in the first place: quantum mechanics. In the universe's first fleeting moments, microscopic quantum fluctuations, tiny jitters in the fabric of space-time, were stretched to cosmic scales by inflation, becoming the density variations frozen into the CMB. That means the largest structures we see today owe their existence to subatomic randomness, magnified across the entire observable universe. It's a staggering thought. The grand design of galaxies and voids was written by the tiniest possible scribble of quantum uncertainty, blown up to proportions beyond human imagination. So the next time you hear about the CMB's near-perfect smoothness, remember, it's the imperfections that make it profound. Those faint ripples are the universe's way of leaving itself a note, a reminder that even in the most uniform beginnings, the seeds of complexity were always there, waiting to unfold. For centuries, astronomers argued over the age of the universe with little more than guesswork. Some estimates placed it at just a few billion years, while others suggested it might stretch back indefinitely. Then came the cosmic microwave background, a celestial stopwatch frozen in time. Thanks to space missions like WMAP and Planck, which mapped the CMB's subtle fluctuations with unprecedented precision, we finally pinned down the universe's age to an astonishingly exact 13.8 billion years. The secret lies in the CMB's geometry. Picture the early universe as a bell struck at the moment of recombination, ringing with density waves that left distinct peaks in the radiation's temperature variations. These peaks act as cosmic yardsticks. The first major peak, for instance, reveals the universe's curvature. If space were positively curved like a balloon, distant CMB hotspots would appear larger, if negatively curved, smaller. Instead, WMAP and Planck found they matched the expected size for a perfectly flat universe, meaning its total mass and energy balance out to near zero curvature. That flatness, combined with the measured rate of expansion, became the cornerstone for calculating cosmic age. But the CMB didn't just hand us a number, it cross-checked it against other cosmic clues. The abundance of light elements like hydrogen and helium, forged in the Big Bang's first minutes, aligns perfectly with the CMB's timeline. Even the oldest known stars, their ages measured through stellar evolution models, fit snugly within the 13.8 billion year framework. It's as if the universe left multiple synchronized clocks all ticking in unison. Planck's data took it further, refining the margin of error to just 50 million years, a blink in cosmic terms. To grasp how precise that is, imagine compressing the universe's lifespan into a single year. 50 million years would equal less than 2 days. That's like pinpointing your birth date down to the hour. Yet the real triumph isn't just the number, it's what it tells us about the universe's fate. A 13.8 billion year age coupled with the CMB's flatness implies dark energy dominates cosmic expansion, accelerating the universe toward an ever cooler, lonelier future. The CMB didn't just measure time, it framed our story within a vast, expanding tapestry with a beginning, a middle, and an inevitable end. So the next time someone asks how old everything is, remember, the answer is written in microwaves, a fossilized heartbeat echoing across 13.8 billion years. Imagine trying to measure the shape of something you're standing inside, no outside perspective, no edges to trace. That's the puzzle cosmologists faced when probing the universe's geometry. Then came the cosmic microwave background, offering a brilliant workaround. It's not just light, it's the universe's own curvature test. By analyzing the CMB's temperature fluctuations, those faint hot and cold spots, scientists uncovered something revolutionary. The cosmos isn't curved like a balloon or warped like a saddle. It's flat, almost perfectly so, to within a razor-thin margin of error. How does a glow from the early universe reveal something so fundamental? It all comes down to angular size. Picture the largest hot spots in the CMB as cosmic yardsticks. If space had positive curvature, like the surface of a sphere, light rays would converge, making distant hotspots appear larger than they really are, just like how Greenland looks comically oversized on a globe. Negative curvature, like a saddle, would do the opposite, squeezing their apparent size. But when satellites like WMAP and Planck mapped these spots, they matched the exact scale predicted for a flat universe. The CMB's patterns didn't stretch or shrink. They were pristine, undistorted, a cosmic fingerprint confirming that parallel lines on the grandest scales stay parallel. This flatness isn't just a geometric quirk, it's a cosmic balancing act of staggering precision. For the universe to be this flat after 13.8 billion years of expansion, its density at the Big Bang must have been fine-tuned to within 1 part in 10 to the power of 60. That's like balancing a pencil on its tip so perfectly it stays upright for billions of years. Such unnatural exactitude baffled scientists until inflation theory offered an explanation. The universe didn't start perfectly balanced. It was stretched flat in the first fraction of a second, ironed out by exponential expansion. But here's where it gets even stranger. A flat universe doesn't mean space is infinite, just that it could be. Think of it like a piece of paper, flat and boundless, whether it's a note card or an endless sheet. The CMB can't tell us if the cosmos loops back on itself like a video game level or stretches forever. But it does confirm that Euclid's ancient geometry, the math we learn in school, holds true across the vastness of space. The implications ripple outward. A flat universe directly shapes its fate. Too much mass and gravity would eventually reverse expansion in a big crunch. Too little and everything would fly apart into icy isolation. Flatness means the cosmos is perfectly poised between these extremes, but with a twist. The CMB also reveals that ordinary matter and dark matter alone can't account for this balance. Something else, dark energy, must make up the difference, pushing the universe toward eternal expansion. So when we say the universe is flat, we're not just describing its shape. We're reading a cosmic ledger written in microwaves that tallies up everything that exists, visible and invisible, and reveals the precarious, beautiful equilibrium that lets galaxies, stars, and us exist at all. The cosmic microwave background holds a startling secret. It's not just a relic of the past, but a crystal ball revealing the universe's accelerating fate. Hidden within its large-scale patterns are the fingerprints of dark energy, the mysterious force pushing galaxies apart faster than gravity can pull them together. When scientists first mapped the CMB's subtle temperature variations, they noticed something odd. The largest ripples across the sky were slightly smaller than predicted. This wasn't a measurement error, it was a cosmic clue. The explanation lies in how dark energy warps the fabric of spacetime. During the universe's first few 100,000 years, matter and radiation dominated, causing space to expand at a steadily slowing rate. But around 5 billion years ago, dark energy, an inherent property of empty space itself, began outweighing gravity's pull, triggering an epoch of runaway expansion. That acceleration stretched the wavelengths of CMB photons traveling to us, subtly squeezing the apparent size of those primordial density fluctuations. The effect is tiny but measurable, like watching distant streetlights shrink as you speed away from them. What's astonishing is how precisely the CMB quantifies dark energy's grip. By combining its data with supernova observations, scientists calculated that dark energy makes up roughly 68% of the universe's total energy budget, a number that aligns eerily well with Einstein's long-abandoned cosmological constant. The CMB doesn't just hint at dark energy's existence. It pins down its influence with the precision of a cosmic accountant, revealing exactly when it began steering the universe's expansion. Yet the real shocker is how early this shadowy force left its mark. Even though dark energy only recently became dominant, its subtle pressure was already at work during recombination. The CMB's pattern of hot and cold spots encodes a memory of that latent push, a whisper of the acceleration to come. It's as if the infant universe knew its fate, leaving behind an encrypted message for future cosmologists to decode. Perhaps most unsettling is what this means for the far future. If dark energy's influence keeps growing, the universe won't just expand, it will tear apart, leaving the CMB as one of the last detectable remnants of a vanishing cosmic dawn. For now, though, those microwaves are more than an echo. They're a warning written across the sky, telling us that the universe's fate was sealed before the first star ever flickered to life. The cosmic microwave background doesn't just glow, it twists. Beyond its temperature variations, the CMB carries another layer of hidden data: polarization, a subtle directional preference in its light waves that acts like a cosmic fingerprint of the universe's most violent birth pangs. This isn't ordinary polarization like sunlight reflecting off a lake. It's a relic of the primordial chaos, a whisper of gravitational waves that rippled through space-time moments after the Big Bang. Here's how it works. When the CMB first broke free during recombination, its photons didn't just stream outward, they scattered off electrons in the seething plasma of the early universe. That scattering left an imprint, like a gust of wind aligning fallen leaves in a specific pattern. Scientists categorize this polarization into two types: E modes and B modes. E modes, the easier to detect, arise from density fluctuations, the same ones that seeded galaxies. But B modes, they're the holy grail. These swirling, curl-like patterns can only be created by gravitational waves, the literal stretching and squeezing of spacetime itself during inflation, the universe's explosive first fraction of a second. Detecting B modes is like listening for the echo of a scream in a hurricane. The signal is astonishingly faint, buried under interstellar dust and the distortion of intervening galaxies. In 2014, the Bicep 2 team thought they'd found it, a faint swirl in the CMB's polarization near the southern celestial pole. The announcement sent shockwaves through cosmology. If confirmed, it would be direct evidence of inflation, proof that the universe expanded faster than light in its infancy. But the celebration was short-lived. Further analysis revealed the signal was partly contaminated by cosmic dust, a humbling reminder of how delicate this hunt truly is. Yet the quest continues. Telescopes like the Simon's Array and future missions aim to tease apart the false signals from the real deal. Why go to such lengths? Because B modes aren't just another data point. They're a time machine to energies 1 trillion times higher than anything achievable in particle colliders. If found, they'd reveal the conditions of the universe at 10 to the power of -36 seconds old, a realm where gravity and quantum mechanics collide. They might even hint at the existence of cosmic strings, defects in spacetime left over from the Big Bang, or extra dimensions folded into the fabric of reality. The CMB's polarization isn't just light, it's a cipher. Every twisted photon carries a message from the universe's first tremors, a story written in the warping of spacetime itself. And we're only just learning how to read it. Think of the cosmic microwave background as the ultimate laboratory, one where physicists can run experiments on the universe's first moments without ever leaving Earth. The light we detect today is more than just a fossil. It's a high-precision time capsule, encoding details about a time so early that even the most powerful particle colliders can't recreate its conditions. The key, those faint temperature fluctuations and polarization patterns aren't just static, they're the universe's own experiment logs, recording what happened when reality was less than a second old. Take cosmic inflation, the theory that the universe underwent a faster-than-light expansion in its first sliver of existence. Without the CMB, inflation would just be a clever idea. But when scientists analyzed the CMB's patterns, they found something extraordinary. The distribution of hot and cold spots matched inflation's predictions with uncanny precision. Inflation would have stretched quantum fluctuations' tiny spacetime jitters into cosmic-scale density variations, leaving behind the exact ripple pattern we see in the CMB today. It's like finding a fossilized footprint that perfectly fits a dinosaur we've only ever imagined. But the CMB doesn't just confirm inflation, it lets us test its specifics. Different inflation models predict subtle differences in the CMB's polarization, particularly those elusive B modes. Some theories suggest inflation was driven by a single quantum field, while others propose a chaotic cascade of energy transitions. By measuring the CMB's fine-grained details, physicists can rule out some models and refine others, effectively reverse engineering the universe's birth mechanics. It's as if the universe left behind a puzzle, and the CMB holds the pieces we need to solve it. And inflation isn't the only theory under scrutiny. The CMB also tests ideas about dark matter's properties, the nature of dark energy, even the possibility of parallel universes. For example, certain anomalies in the CMB, like the infamous cold spot, have sparked wild speculation. Could it be evidence of a collision with another bubble universe during inflation? Or a cosmic defect left over from higher dimensional physics? The CMB doesn't just answer questions, it dares us to ask weirder, bolder ones. What makes this time machine so powerful is its impartiality. Unlike human experiments, the CMB wasn't designed to fit any theory. It's raw data, unedited by bias, waiting for us to decode its secrets. Every new map, every finer measurement peels back another layer, revealing glimpses of a time when the laws of physics as we know them were still taking shape. The CMB is more than a window to the past, it's a mirror reflecting how much we've yet to learn. Buried in the cosmic microwave background's near-perfect uniformity lies a celestial oddity so bizarre it defies conventional explanation. A sprawling cold spot stretching over 1 billion light-years, where the temperature dips just a fraction lower than the surrounding glow. At first glance, it might seem like a statistical fluke, a cosmic typo in an otherwise flawless manuscript, but some scientists suspect it's something far stranger. A bruise left by a collision with another universe. This isn't science fiction. The multiverse hypothesis, the idea that our universe is just one bubble in an infinite froth of parallel realities, gains traction when we confront anomalies like the cold spot. According to inflationary theory, other universes could have formed alongside ours during the Big Bang, each with its own distinct physics, separated by expanding space-time. If one of these bubbles brushed against ours in those chaotic early moments, the gravitational tug of war could have left a scar in the CMB, a region where photons lost a tiny bit of extra energy as they traveled through the warped boundary between worlds. What makes the cold spot so tantalizing is its statistical improbability. When scientists ran simulations of the CMB based on our standard model of cosmology, regions that large and that cold appeared less than 2% of the time. It's like rolling a die 100 times and getting the same improbable number far more often than chance should allow. Of course, skeptics argue it could just be a vast supervoid, a cosmic desert with fewer galaxies absorbing some of the CMB's energy along our line of sight. But here's the catch: surveys haven't found a void large or empty enough to explain the temperature drop. The mismatch keeps the multiverse theory alive. Yet the cold spot isn't the only anomaly fueling the fire. The CMB also exhibits puzzling asymmetries. One hemisphere of the sky is slightly warmer than the other, and certain large-scale patterns align in ways that defy randomness. These axis of evil quirks, as scientists wryly dub them, could be artifacts of our observational limits or fingerprints of a neighboring universe's gravitational influence, gently tugging ours out of symmetry. The real proof, though, might lie in the CMB's polarization. If another universe truly grazed ours, it could have generated unique gravitational waves, imprinting a telltale swirl in the polarization patterns we've yet to detect. Future telescopes, like the proposed Light-Bird satellite, could hunt for these subtle distortions, turning speculation into testable science. For now, the cold spot remains a mystery wrapped in microwaves. It could be a statistical mirage, a flaw in our models, or something far more profound, a crack in the windowpane of reality, offering a fleeting glimpse into the infinite beyond. Whether it's proof of parallel worlds or just cosmic noise, one thing's certain: the CMB keeps whispering secrets we're only beginning to decipher. The cosmic microwave background isn't just a silent glow, it's a symphony. Those faint temperature fluctuations we've been exploring, they're not random static. They're the fossilized echoes of sound waves that once rippled through the universe's seething plasma, a cosmic bassline from a time when space itself was ringing like a bell. Picture the early universe as a colossal, ultra-dense fluid, a roiling soup of protons, electrons, and light, all packed so tightly that photons couldn't travel far before bouncing off particles. In that superheated chaos, gravity pulled matter inward while radiation pressure pushed it outward, creating pulses of compression and rarefaction, literal sound waves vibrating through the cosmos. These weren't gentle hums, they were deafening, planet-shattering booms propagating at over half the speed of light. But unlike sound on Earth, which travels through air, these waves moved through a medium of ionized gas and energy, leaving their imprint on the fabric of space-time itself. Then came recombination, the moment the universe cooled enough for atoms to form. Suddenly, light broke free, and those sound waves froze mid-vibration, etching their peaks and troughs into the CMB-like grooves on a cosmic record. The hot spots we see today, they're regions where plasma was compressed, the crests of those primordial sound waves. The cold spots, the troughs where matter had spread thin. It's as if the universe pressed pause on its own soundtrack, preserving those oscillations for us to decode billions of years later. What's astonishing is the scale. The most prominent note in this cosmic chord, the first acoustic peak, corresponds to waves that had just enough time to travel about 450,000 light-years before recombination. That's a wavelength so vast it could wrap around our galaxy 5 times over. But here's the mind-bending part: that distance isn't arbitrary, it's a measuring stick. By analyzing how these sound wave imprints vary across the sky, scientists can calculate the universe's curvature, density, and even the speed at which those waves propagated, revealing the exact mix of ordinary matter, dark matter, and radiation in the infant cosmos. This sound wave snapshot also solves a puzzle that once baffled astronomers: why galaxies cluster at specific intervals. Those oscillations didn't just vanish after recombination. Gravity took over, amplifying the denser regions into the cosmic web we see today. The spacing between galaxy superclusters, it mirrors the wavelength of those ancient sound waves, a ghostly rhythm stretching across billions of light years. Yet the real marvel is how crisply these waves survived. Most sounds fade, absorbed by walls or dissolved into noise. But in the near-perfect vacuum of space, with no medium to scatter them, those primordial vibrations stayed pristine, untouched for over 13 billion years until we pointed our telescopes skyward. It's as if the universe left us a voicemail from its infancy, and we're only now pressing play. So the next time you hear a musical note, remember the cosmos once sang too. And its deepest secrets are still vibrating in the silence between the stars. What we call the cosmic microwave background today wasn't always microwaves. In fact, when this light first broke free, it blazed across the cosmos as blinding visible light, as bright and hot as the surface of a star. The photons we now detect as faint whispers in the microwave band began their journey as searing gamma rays, packed with so much energy they could slice through solid lead. Over 13.8 billion years, the relentless expansion of space stretched these photons thousands of times longer, redshifting their wavelengths from the violent blues of newborn creation to the frigid hum we measure today. Think of it like a cosmic rubber band. At recombination, when the universe became transparent, CMB photons had wavelengths around 1,000 times shorter than they are now, comparable to the warm glow of a lightbulb filament. But as space stretched, those wavelengths stretched with it, like ink smearing across an ever-expanding canvas. By the time this light reached modern telescopes, it had redshifted all the way into the microwave range, around 1 to 10 millimeters long, the same wavelength your microwave oven uses to heat leftovers. That's why we call it the cosmic microwave background, not because it started as microwaves, but because expansion dragged it there. Here's what's wild. If you could rewind the universe's expansion like a film in reverse, the CMB wouldn't just brighten, it would change color before your eyes. Around 50 million years after the Big Bang, its light would shine in the ultraviolet. A few 100 million years later, it would glow orange like a sunset. By the time the first galaxies ignited, it had already faded to infrared, invisible to human eyes. Today, we need radio telescopes to detect it at all. The CMB is the ultimate example of cosmic aging, a once vivid signal dimmed by time and distance into near oblivion. This redshift isn't just a curiosity, it's proof of the universe's expansion written in light. Edwin Hubble first noticed galaxies redshifting as they raced away from us, but the CMB shows something even more profound. All of space itself is stretching, carrying ancient light along for the ride. Those microwaves we detect today are more than relics. They're mile markers showing exactly how far the cosmos has expanded since its infancy. And if dark energy keeps accelerating that expansion, future astronomers might not detect the CMB at all. Its wavelengths could stretch into undetectable radio waves, erasing the afterglow entirely. Yet for now, that redshifted light is a gift. It's why we can study the CMB without being blinded by its original intensity. If those photons hadn't cooled to microwaves, they'd outshine every star in the sky, drowning out all other cosmic signals. Instead, they linger like a fading echo, just strong enough to decode but gentle enough to let newer light, the light of galaxies, supernova, and life, take center stage. The universe didn't just leave us a message, it lowered its voice to a whisper, letting us listen when we were finally ready. Even the cosmic microwave background, that near-perfect echo of the Big Bang, has its quirks, and none are more baffling than what scientists half-jokingly call the axis of evil. This isn't some cosmic supervillain's doing, but a bizarre pattern in the CMB that stubbornly refuses to fit our tidy models of how the universe should behave. When researchers mapped the largest temperature fluctuations across the sky, they noticed something unsettling. Certain hot and cold spots seemed eerily aligned along a particular plane, as if the universe had a hidden equator where its anomalies lined up like cosmic breadcrumbs. This alignment defies one of cosmology's sacred principles, the idea that the universe should look roughly the same in all directions, no matter where you're observing from. Called the Copernican principle, it's the reason we don't assume Earth holds some privileged position in the cosmos, but the axis of evil throws a wrench into that assumption. The odds of such a large-scale alignment happening purely by chance, less than 1 in 1,000. Some researchers dismiss it as a statistical fluke or an artifact of incomplete data, but others wonder if we're seeing cracks in our understanding of the universe's very foundation. One radical explanation ties back to inflation, the theory that the early universe expanded exponentially faster than light. If inflation wasn't perfectly uniform, if some regions stretched more than others, it could have left behind a preferred direction imprinted in the CMB. Another, even more speculative idea suggests the axis might be a gravitational bruise from a collision with another universe during inflation, warping our cosmos like a fingerprint pressed into wet clay. Then there's the unsettling possibility that we're seeing evidence of a pre-Big Bang structure, some remnant of whatever existed before our universe began, a cosmic fossil older than time itself. But before we rewrite physics, there's a humbler explanation: contamination. Our solar system's motion through the CMB creates a Doppler shift, slightly warming one hemisphere of the sky and cooling the other. Subtracting this effect is notoriously tricky, and some argue incomplete corrections could leave behind artificial patterns. Even the Milky Way's magnetic field or vast, unseen clouds of interstellar dust might be scattering CMB photons in ways we haven't fully accounted for. Yet after all these checks, the axis persists. Future telescopes like the Simons Observatory aim to measure it with unprecedented precision, either confirming its reality or exposing it as a grand illusion. Either outcome would be profound. If the axis is real, it hints at physics beyond our current theories, a cosmic asymmetry woven into the fabric of reality. If it vanishes under sharper scrutiny, it'll stand as a cautionary tale about how even our best data can play tricks on us. For now, the axis of evil remains one of cosmology's great open questions, a whisper that the universe might still be keeping its strangest secrets close. What if the cosmic microwave background isn't just a relic, but a cosmic billboard, a beacon left by or for intelligences beyond our own? It might sound like science fiction, but some scientists argue the CMB's unique properties make it the ultimate universal reference point, a natural lighthouse in the darkness between galaxies that any advanced civilization could use to communicate or navigate. Think about it, unlike stars or quasars which flicker and fade, the CMB is everywhere, unchanging on human timescales and detectable from any point in the universe. If you wanted to send a message across billions of light years, encoding it in subtle modulations of this primordial background might be the most reliable way to ensure it's found. Here's how it could work. The CMB's temperature fluctuations aren't entirely random, they follow mathematical patterns like peaks and valleys in a cosmic fingerprint. An advanced civilization could artificially alter these patterns in specific regions, embedding signals in the microwave background itself. Imagine tweaking the polarization of CMB photons in a precise sequence, creating a binary code visible to anyone with sensitive enough telescopes. These wouldn't be radio broadcasts fading over distance, but permanent etchings on the fabric of reality, detectable as long as the CMB persists. Navigation is another tantalizing possibility. The CMB's dipole anisotropy, a subtle hot and cold asymmetry caused by our Milky Way's motion through space, acts like a cosmic compass, revealing direction relative to the universe's expansion. For a species traversing intergalactic distances, such a universal reference frame would be invaluable. Just as ancient mariners used the stars, a spacefaring civilization might calibrate their warp drives or wormhole trajectories using the CMB's temperature gradients, treating it as the ultimate GPS. And here's the spine-tingling part. We might already have the tools to find such signatures. Projects like the Breakthrough Listen initiative, which scans the cosmos for artificial signals, could repurpose their algorithms to sift through CMB data for non-random anomalies. Unexplained geometric patterns in polarization or improbable temperature symmetries might not be glitches, they could be deliberate markers. A cosmic X marks the spot, left by someone who knew we'd one day look up. Of course, skeptics dismiss this as speculation. The CMB's uniformity is nearly perfect, and any artificial tweaks would require staggering energy expenditures. But consider this, human civilization has barely scratched the surface of cosmology. A species millions of years more advanced might see manipulating the CMB as trivial. After all, we're already detecting gravitational waves and imaging black holes, technologies that would have seemed magical a century ago. If the universe teems with intelligence, the CMB could be their oldest, most enduring handshake, a message not in a bottle but in the echo of creation itself. So the next time you see a CMB map, remember, those splotches of hot and cold might not be random noise. They could be the universe's first guestbook waiting for us to read between the lines. A cosmic microwave background doesn't just passively fill the universe, it actively shapes the light passing through it, leaving ghostly fingerprints on even the most energetic radiation. When high-energy gamma rays, those violent bursts of light flung from supernova or colliding black holes, travel across the cosmos, they don't journey alone. They collide with the CMB's sea of microwaves in a spectacular subatomic showdown, and the aftermath reveals secrets about the hidden magnetic fields woven between galaxies. Here's how this cosmic shadow play works. Gamma rays are so energetic that when they meet a CMB photon, they can spontaneously transform into an electron and its antimatter twin, a positron, in a process called pair production. It's like two cars smashing together and instantly forging new vehicles from the wreckage. But here's the twist, those newly born particles don't just vanish. They spiral along interstellar magnetic fields, radiating their own light in a process called inverse Compton scattering. By the time this secondary glow reaches us, it carries a faint but detectable imprint of those otherwise invisible magnetic fields, a trail of breadcrumbs left by gamma rays that never made it here intact. This phenomenon isn't just theoretical. Telescopes like the Fermi Gamma Ray Space Telescope have spotted distant blazars, supermassive black holes spearing jets of gamma rays toward Earth whose light dims in precise ways as it battles the CMB. The amount of dimming tells us how thick the fog of CMB photons is along that path, while the scattered light's polarization hints at the strength and structure of the magnetic fields it traversed. It's as if the CMB and gamma rays are dancing partners, their steps revealing the universe's hidden choreography. What makes these shadows so valuable is their scale. Magnetic fields between galaxies are fiendishly hard to study directly. They don't emit light, and their effects are subtle. But gamma rays, boosted by the CMB's interference, act like cosmic flashlight beams, illuminating these invisible force lines across millions of light years. Some of these fields may trace back to the universe's turbulent youth, fossilized remnants from when galaxies first ignited. Others could be woven by the cosmic web's vast currents, where dark matter's gravitational pull funnels ionized gas into magnetic rivers. Perhaps the most startling revelation is how ordered these fields appear. Instead of chaotic tangles, many stretch coherently across mind-bending distances, as if the universe had a primordial loom weaving symmetry into the void. That orderliness challenges our understanding of how magnetic fields form. Did they arise from tiny seed fields stretched by cosmic inflation, or were they forged later, stirred by the whirlpool motions of collapsing galaxies? The CMB's shadow on gamma rays is helping settle that debate, one scattered photon at a time. So while the CMB might seem like a relic, it's also a cosmic probe, turning high-energy light into a tool for mapping the universe's hidden forces. Those microwaves aren't just background noise, they're the universe's way of developing its own film, revealing structures no telescope could see alone. Every gamma ray that fades or flickers carries a message. The past isn't just something we observe, it's something we interact with, and the CMB is the mediator, quietly reshaping the light of the present to reveal the secrets of the past. What if our universe isn't the first or the last to exist? The cosmic microwave background might hold clues to an even more radical idea, that the Big Bang wasn't a true beginning but a cosmic reset, one in an endless cycle of universes being born, dying, and reborn. This isn't just poetic speculation. Some versions of string theory and quantum gravity suggest that remnants of a previous universe could be imprinted in the CMB's faintest patterns, like shadows on a cave wall. Take the concept of cyclic cosmology, proposed by physicists like Paul Steinhardt and Neil Turok. In their model, the universe undergoes endless epochs of expansion and contraction, each beginning with a big bang and ending in a big crunch. But here's the twist: these cycles aren't perfect copies. Each iteration leaves behind subtle scars, gravitational waves, topological defects, or even variations in dark energy that could linger in the CMB. Imagine two sheets of paper pressed together. When pulled apart, faint ink stains might transfer. Similarly, a pre-Big Bang universe might have stained ours with anomalies that defy conventional explanation. The most tantalizing evidence, those infamous CMB anomalies, the cold spot, the axis of evil, or large-scale patterns that seem too structured for randomness. Could these be cosmic bruises from a collision with a previous universe's bubble, or echoes of quantum fluctuations that carried over from an earlier cycle? Some models even predict concentric rings in the CMB's polarization, maps ripples from gravitational waves generated by a universe that came before ours, like ripples from a pebble tossed into a pond before it froze. Critics argue these ideas flirt with the untestable. After all, if a prior universe left traces, how do we distinguish them from quirks of our own cosmic infancy? But here's where the CMB becomes a time machine. Future telescopes hunting for primordial gravitational waves could spot signatures unique to cyclic models, swirls in the polarization patterns that inflation can't explain. And if the universe's dark energy density varies in ways that suggest a memory of past cycles, the CMB's large-scale fluctuations might hold the receipt. The wildest implication: if cyclic cosmology is correct, the CMB isn't just our origin story, it's a palimpsest layered with fragments of universes long gone. Each cycle's physics might differ slightly, meaning the laws we take for constant, the speed of light, the strength of gravity, could be relics of a previous universe's death throes. The CMB, then, isn't a snapshot, it's a collage, and we're only just learning how to peel back the layers. So while we marvel at the CMB's near-perfect uniformity, its imperfections might be the most exciting part. They're not just noise, they're potential whispers from a time before time, hints that our universe is just one page in an infinite cosmic library. And if we're lucky, the next generation of sky maps will teach us to read between the lines. Hold your hand out the window of a moving car and you'll feel the wind rush past, a simple reminder that motion isn't just something you do, it's something you feel. The universe has its own version of this phenomenon, written in the cosmic microwave background. What looks like a perfectly uniform glow isn't quite so uniform after all. In fact, it's slightly warmer in one direction and cooler in the opposite, a subtle but unmistakable pattern called the dipole anisotropy. This isn't a flaw in the cosmos, it's a cosmic speedometer, revealing our own Milky Way's breakneck journey through the universe. Here's how it works. Imagine you're running through rain. Even if the raindrops are falling straight down from your perspective, they'll seem to slant toward you because of your forward motion. The CMB's photons behave the same way. As the Milky Way hurtles through space at roughly 600 kilometers per second, yes, per second, the CMB's microwaves appear slightly blue-shifted and thus warmer in the direction we're moving, while those behind us get red-shifted cooler. The result, a temperature difference of about 3.3 millikelvin, a faint but measurable fingerprint of our galaxy's velocity. But here's what's wild. This dipole isn't just about our motion relative to the CMB. It's a cosmic chain reaction of movement. The Milky Way orbits the center of our local group of galaxies, which itself is being pulled toward the Virgo cluster, which in turn is falling toward the monstrous gravitational pull of the Great Attractor, a mysterious concentration of mass hundreds of millions of light-years away. The CMB dipole captures the sum of all these motions, a snapshot of our galaxy's place in an immense cosmic tug-of-war. And there's a twist. When scientists subtract our galaxy's motion from the dipole, they're left with another curious signal. The CMB appears to have its own intrinsic dipole, separate from our movement. Some theories suggest this might hint at primordial gravitational waves or even large-scale anomalies in the universe's structure. Others wonder if it's a glimpse of something deeper, a relic of the universe's turbulent infancy, when the fabric of spacetime itself was still settling into equilibrium. So the next time you hear about the CMB's near-perfect uniformity, remember, perfection is relative. That tiny temperature imbalance isn't just noise. It's the universe's way of reminding us that we're not stationary observers but passengers on a galaxy speeding through the cosmos, leaving a faint but indelible wake in the oldest light there is. The cosmic microwave background isn't just a relic. It's the universe's ultimate measuring tape, allowing astronomers to gauge distances across the cosmos with staggering precision. The secret lies in its faint ripples, particularly the imprint of something called Baryon acoustic oscillations, or BAO. These are frozen sound waves from the universe's infancy, trapped in the CMB like echoes in a vast, endless canyon, and they serve as a cosmic ruler stretching billions of light-years long. Picture the early universe as a turbulent ocean, where matter and radiation were locked in a violent tug-of-war. Gravity pulled atoms inward while the pressure of light pushed them outward, creating oscillations, ripples of denser and sparser regions. that propagated outward at nearly 2/3 the speed of light. When the plasma cooled during recombination around 380,000 years after the Big Bang, those waves froze in place, leaving behind a signature pattern in the CMB. The most striking feature, a predictable spacing between those ripples about 500 million light-years today, that acts as a standard ruler. Here's how astronomers use it. When we map galaxies in the modern universe, we find they cluster at intervals that match these ancient sound waves. The BAOs are like cosmic mile markers. By measuring the apparent size of these patterns at different distances, scientists can determine how far away galaxies really are. If a BAO structure appears smaller than expected, it means it's farther away, its light stretched by the expansion of space. If it looks larger, it's closer. It's as if the universe handed us a ruler with perfect, indelible markings, allowing us to measure its growth over billions of years. What makes this cosmic ruler so powerful is its universality. Unlike other distance measuring tools, which rely on specific types of stars or supernova, BAOs are etched into the fabric of the cosmos itself. They're immune to the dimming effects of dust or the quirks of stellar evolution. Whether we're looking at galaxies 10 billion light-years away or just a few 100 million, those oscillations are always there, always the same. That consistency allows scientists to cross-check other distance measurements, refining our understanding of the universe's expansion rate, the Hubble constant, with unprecedented accuracy. But the real magic happens when we combine BAOs with other CMB data. The angular scale of these oscillations in the CMB, how big they appear on the sky, reveals the universe's geometry and energy content. When paired with the clustering of galaxies, they help disentangle the competing influences of dark matter and dark energy, showing how each has shaped cosmic evolution. It's like using a single ruler to measure not just distance but time, density, and even the fate of the universe. Yet BAOs aren't just tools, they're storytellers. Their precise spacing hints at the universe's initial conditions, the density of matter, and the speed of those primordial sound waves. They're a direct link between the CMB's ancient light and the cosmic web we see today, proof that the universe's largest structures grew from the tiniest vibrations. Every galaxy supercluster, every vast void, is a footnote to those oscillations, a reminder that the universe's past is still written in the sky if we know how to read it. So the next time you hear about the CMB's temperature fluctuations, remember, those ripples aren't just cosmic noise. They're the universe's own ruler, etched in microwaves, waiting for us to measure the unmeasurable. Deep within the cosmic microwave background's faint glow lurks an invisible fingerprint, one left not by light, but by particles so elusive they pass through entire planets like ghosts. These are the relic neutrinos, born in the first second after the Big Bang, and the CMB holds them captive in its data like cosmic detective work. While we can't directly observe these ancient neutrinos today, their subtle gravitational influence on the early universe left scars in the microwave background we can now decode. Neutrinos are the universe's ultimate escape artists, nearly massless, chargeless, and barely interacting with matter. A trillion zip through your body every second, leaving no trace. But in the universe's first moments, they were anything but passive. During the initial fireball of the Big Bang, neutrinos outnumbered protons and electrons by 1,000,000,000 to 1, forming a dense, energetic sea that shaped how matter clumped together in those critical early epochs. As the cosmos expanded, these neutrinos streamed freely across space, their slight but measurable gravitational pull tweaking the density fluctuations that later became the CMB's hot and cold spots. This is where the CMB becomes a neutrino time capsule. When scientists analyze the precise statistical patterns of those temperature variations, especially the relative heights of the acoustic peaks, they're effectively weighing the gravitational shadow of primordial neutrinos. The reasoning is elegant. If neutrinos were heavier, their early streaming would have smoothed out small-scale clumps of matter, damping certain peaks in the CMB's power spectrum. Too light, and those peaks would look unnaturally pronounced. The CMB's exact measurements reveal that relic neutrinos must have a combined mass of less than 0.2 electron volts, a whisper-thin value that aligns with particle physics experiments, but now confirmed across cosmic scales. The implications ripple outward. These neutrinos aren't just fossil particles, they're thermal witnesses to the universe's first second. Their presence in the CMB confirms they decoupled from matter even earlier than photons did, just 1 second after the Big Bang, when the cosmos was still a seething plasma hot enough to forge atomic nuclei. Unlike the CMB's photons, which scatter off electrons, neutrinos slipped free unscathed, carrying undisturbed information from an era before atoms existed. Their faint imprint on the CMB is like finding a shadow cast by something long gone, a silhouette of the universe's most infamously slippery particles. But the detective story doesn't end there. The CMB also hints at how many neutrino species exist, a question that once puzzled particle physicists. Early models suggested 3 types: electron, muon, and tau neutrinos. Yet when scientists tallied the CMB's fluctuations, any extra, sterile neutrino species would have altered the cosmic expansion rate during recombination, leaving excess smoothing in the temperature maps. The verdict: the CMB strongly favors 3 neutrino families, matching laboratory findings with cosmic-scale precision. It's as if the universe left a ledger, one where neutrinos, despite being nearly invisible, signed their names in gravitational ink. Perhaps most astonishing is what this means for dark matter. Neutrinos, though abundant, are too light and fast-moving to explain the universe's missing mass. Their CMB signature proves that most dark matter must be something else: slower, colder, and far more mysterious. Without the CMB's ability to weigh and count these ghostly particles, we'd be missing a crucial piece of cosmology's puzzle. So the next time you hear about the CMB's microwaves, remember, they're not just light. They're a neutrino filter, a cosmic sieve that trapped the faintest traces of the universe's most elusive particles. And in their subtle patterns, we're reading the autobiography of a shadow universe, one written in particles that barely exist, yet shaped everything we see. The cosmic microwave background isn't just a window to the past, it's a laboratory for the future of physics, a testing ground where scientists hunt for the holy grail of modern cosmology, a theory of quantum gravity. Hidden in those faint microwaves could be the faintest tremors of spacetime itself, quantum fluctuations from the universe's first moments that might finally bridge Einstein's relativity with the bizarre rules of the quantum world. At the heart of this quest is a glaring paradox. General relativity, which describes gravity as the curvature of spacetime, works flawlessly for planets, stars, and galaxies. Quantum mechanics governing the subatomic realm predicts particle behavior with uncanny precision. But when you try to merge them, to describe how gravity operates at the scale of a single atom, the math explodes into nonsense. This divide isn't just academic. It means we fundamentally don't understand how the universe behaved in its first fraction of a second, when all forces were unified and spacetime was a seething quantum foam. That's where the CMB becomes indispensable. If quantum gravity left any imprint on the universe, it would have done so during inflation, the exponential expansion that stretched quantum fluctuations to cosmic scales. Some theories, like loop quantum gravity or string theory, predict these primordial spacetime jitters would have subtly twisted the polarization of CMB photons, creating unique swirls in the radiation's orientation. These B-mode polarization patterns, if detected, would be the smoking gun of quantum gravity, a direct snapshot of spacetime's granularity at energies 1 trillion times beyond what any particle collider could reach. The challenge: these signals are unimaginably faint, buried under cosmic dust and the cacophony of later universe formation. It's like trying to hear a single note in a symphony played at the edge of the observable universe. Yet experiments like the Simons Observatory and future space missions are pushing detector sensitivity to the brink. searching for these telltale swirls with instruments chilled to near absolute zero to minimize noise. Some models even suggest that certain quantum gravity theories would leave distinct fingerprints in the CMB's statistical anomalies, like the cold spot or axis of evil, hinting at a pre-inflationary phase where spacetime behaved more like a network of interconnected loops than a smooth continuum. What makes this search so thrilling is its stakes. If we find evidence of quantum gravity in the CMB, it wouldn't just validate one theory, it would rewrite our understanding of reality's fabric. Did spacetime emerge from a sea of quantum entanglement? Are there extra dimensions coiled tighter than atoms, imprinting their geometry on primordial light? The answers might be hiding in microwaves older than stars, waiting for us to decipher them. So while the CMB's glow seems like a quiet relic, it's actually a cosmic shout across 14 billion years, one that could finally reveal how the universe stitched together its deepest laws. Every flicker in that ancient light isn't just a whisper from the past. It's a challenge from the universe itself, daring us to solve its greatest puzzle. One of the greatest cosmic detective stories hiding in the cosmic microwave background isn't what's there, but what isn't. When scientists mapped the CMB's temperature fluctuations across the sky, they noticed something bizarre. On the largest scales, the universe seems oddly quiet. The biggest patches of the CMB, spanning more than 60 degrees, show far less variation than our best models predict. It's as if the cosmos forgot to write the first chapter of its own story, leaving a gaping hole where the most fundamental cosmic structures should have begun. This missing large-scale power isn't just a minor anomaly, it's a full-blown crisis for cosmology. According to the Standard Model, the universe's expansion during inflation should have stretched quantum fluctuations into a symphony of waves with peaks and troughs at every conceivable scale. Yet when we look at the CMB's biggest ripples, the music falls silent. The statistical probability of this happening by chance, less than 1 in 1,000. Some researchers dismiss it as a cosmic coincidence, but others wonder if we're seeing the first crack in our understanding of inflation itself. The implications are staggering. If the lack of large-angle correlations is real, it might mean inflation didn't happen quite the way we think. Perhaps the universe didn't inflate uniformly, leaving some regions smoother than others. Or maybe inflation didn't last as long as we've assumed, cutting off the growth of those largest fluctuations before they could fully form. There's even a radical possibility that our observable universe is just a tiny bubble in a far vaster multiverse, and what we're seeing is the edge of our cosmic horizon where the rules subtly change. But before we rewrite physics, there's a humbler explanation. Our instruments might be fooling us. The CMB's largest scales are notoriously hard to measure accurately, contaminated by the Milky Way's glare or subtle calibration errors in telescopes. Even the way we process CMB data, removing the dipole caused by our galaxy's motion, could inadvertently erase some of the signal we're searching for. The Planck satellite's painstaking attempts to account for these factors still left the anomaly intact, but skeptics argue we might need even more precise measurements to settle the debate. Yet if the missing power persists, it could reshape cosmology. Some theories propose that the universe's geometry isn't perfectly flat, but slightly curved on scales larger than we can observe, subtly suppressing those vast fluctuations. Others suggest dark energy wasn't constant but evolved over time, altering the growth of primordial structures in ways we're only beginning to comprehend. The most haunting possibility, that we're seeing evidence of a pre-Big Bang era, a shadow of whatever came before inflation, imprinted on the CMB like a palimpsest. For now, the silence lingers, an unanswered question written in microwaves. Whether it's a flaw in our models, a limitation of our tools, or a clue to something profoundly new, one thing's certain: the universe's quietest corners might be shouting its loudest secrets. We just have to learn how to listen. What if the cosmic microwave background is hiding more than just the secrets of our universe? What if it's whispering about realities beyond our own? Among the most tantalizing possibilities is that anomalies in the CMB could be the first clues to extra dimensions, hidden layers of space curled so tightly they're invisible to us, yet leave faint fingerprints in the oldest light we can see. Think of it like this: if our universe were a sheet of paper, we'd only experience its length and width. But if that paper had microscopic folds, tiny, curled-up dimensions too small to see, energy and particles moving through them would leave subtle traces. The CMB, as the universe's most pristine fossil, might encode these traces in its temperature fluctuations or polarization patterns. Some theories, like string theory, propose that extra dimensions are necessary to unify physics at the quantum level. If true, the violent environment of the early universe could have stretched these dimensions briefly, imprinting their geometry onto the CMB before they collapsed back into invisibility. The most compelling evidence might lie in the CMB's statistical oddities. Certain large-scale anomalies like the cold spot or the axis of evil defy predictions based on our three-dimensional understanding of space. One radical explanation: these could be gravitational echoes from higher dimensional structures brushing against our universe during inflation. Imagine dropping a pebble into a pond, but the ripples behave strangely because unseen currents beneath the surface are tugging at them. Similarly, hidden dimensions could warp the CMB's fluctuations in ways that look off to our 3D-bound instruments. Even more intriguing is the role of primordial black holes. Some models suggest these tiny, hypothetical black holes formed in the early universe could be portals to higher dimensions. Their evaporation via Hawking radiation might have left unique signatures in the CMB's polarization swirls or hotspots that don't fit standard cosmology. Future telescopes hunting for these patterns could stumble upon proof that gravity, which appears weak in our dimensions, is actually spilling into others. But the real smoking gun would come from gravitational waves. If extra dimensions exist, the inflationary period's violent stretching of space-time could have generated a distinct spectrum of gravitational waves, imprinting a telltale twist in the CMB's B-mode polarization. Unlike the usual inflationary signals, these would carry the shape of higher dimensional geometry, like a shadow cast by a hidden object. Experiments like the upcoming Lightbird mission are designed to spot such nuances with unprecedented precision. Of course, skeptics argue these ideas are untestable fantasy masquerading as physics. Yet the CMB has surprised us before. What began as a faint hiss in a radio antenna rewrote cosmology. Now, as we probe its subtlest ripples, we're not just studying our universe's birth. We might be glimpsing the contours of realities we can't yet imagine, where space has more layers than we can see, and the CMB is our only map to the unseen. So the next time you gaze at a CMB map, remember, those splotches of hot and cold might not just be relics. They could be messages from dimensions waiting to be discovered, folded into the fabric of space itself. And if we're right, the universe is far stranger and far bigger than we ever thought. The cosmic microwave background might be the ultimate reference frame, a stationary backdrop against which all cosmic motion should be measured, but something is throwing that assumption into chaos. Astronomers call it dark flow, a bizarre phenomenon where entire galaxy clusters, thousands of them, appear to be moving in a coordinated rush toward a single patch of sky, as if tugged by something vast and unseen beyond the edge of our observable universe. This isn't just random drift, it's a cosmic current moving at over 2 million miles per hour, and it defies everything we know about how the universe should behave. Here's what makes dark flow so unsettling. According to the standard model of cosmology, the universe's expansion should distribute matter and energy evenly on the largest scales, meaning there shouldn't be any preferred direction for galaxies to move beyond local gravitational pulls. Yet when scientists studied the motion of galaxy clusters using the CMB as a reference, they found something inexplicable. the cluster's hot gas measured via the Sunyaev-Zeldovich effect, a subtle distortion they imprint on CMB photons, revealed a bulk flow that shouldn't exist. It's like watching leaves scattered on a pond suddenly all drift toward one shore, ignoring the wind. The leading theory, a gravitational anomaly so colossal it lies beyond our cosmic horizon. Imagine a supermassive structure, a supervoid, or an overdense region of space-time so enormous that its gravity permeates the observable universe, pulling everything toward it like a hidden magnet. Some models suggest it could be a remnant of pre-inflationary physics, a scar from when the universe was smaller than an atom. Others propose it's evidence of a neighboring universe in the multiverse, its gravity leaking into ours through higher dimensions. Either way, the dark flow hints that our cosmic neighborhood might be just a small corner of something far larger and stranger. Critics argue the data might be skewed, perhaps by incomplete cluster samples or unresolved distortions in the CMB itself. But the signal persists across multiple studies, even as instruments improve. The Planck satellite's data, for instance, initially seemed to dampen the dark flow's significance, but deeper analysis revealed the anomaly still lingered at smaller scales. It's as if the universe is teasing us with half-answers, refusing to let go of the mystery. What's at stake isn't just a quirky observation. If dark flow is real, it could rewrite our understanding of cosmic inflation. Maybe the early universe wasn't perfectly uniform, and some regions expanded faster than others, leaving behind imbalanced gravitational echoes. Or perhaps dark energy isn't uniform, but clustered in ways that nudge galaxies en masse. The most radical possibility, that we're seeing the first hints of a cosmic preferred frame, a directionality to space itself that Einstein's relativity never accounted for. For now, dark flow remains one of cosmology's great open questions, a ghostly current in the cosmic dark. Whether it's a flaw in our measurements, a statistical mirage, or a window into realms beyond our sight, one thing's certain: the CMB isn't just a relic of the past. It's a compass pointing toward mysteries we're only beginning to fathom. The cosmic microwave background does more than illuminate the past, it casts a shadow. Not from light, but from gravity. As those ancient photons travel across the cosmos to reach us, they don't move in straight lines. Instead, they bend and twist, warped by the invisible scaffolding of dark matter that permeates the universe. This phenomenon, called gravitational lensing, transforms the CMB into the ultimate dark matter detector, revealing the unseen architecture of reality itself. Imagine the CMB as a spotlight shining through a dense forest. You can't see the trees directly, but their shadows ripple across the ground, betraying their presence. Dark matter works the same way. Though it emits no light and barely interacts with ordinary matter, its gravitational pull is relentless. When CMB photons pass through vast clouds of dark matter, structures like galaxy clusters or the filaments of the cosmic web, their trajectories curve ever so slightly. The effect is minuscule, a deflection of just a few arc minutes, but modern telescopes like the Planck satellite and the Atacama Cosmology Telescope can measure these distortions with jaw-dropping precision. What's astonishing is how these lensing patterns map the universe's skeleton. By analyzing the CMB's subtle smearing, scientists reconstruct where dark matter clumps and how it's distributed across billions of light years. The resulting maps confirm something eerie. Dark matter isn't just scattered randomly. It forms an intricate web-like structure with dense nodes where galaxies cluster and vast voids where almost nothing resides. These blueprints match computer simulations of cosmic evolution almost perfectly, validating decades of theory. But the CMB's lensing data goes further. It weighs dark matter directly. Unlike methods that infer its presence from galaxy rotations or collisions, gravitational lensing measures dark matter's pull in pristine regions of space, far from the messy physics of stars and gas. The verdict, dark matter outweighs visible matter by a factor of 5 to 1, a ratio etched into the CMB's warped light. It even reveals how dark matter behaves, cold, slow-moving, and utterly unlike any known particle. The real magic happens when combining lensing with the CMB's other secrets. The acoustic peaks, those frozen sound waves from the early universe, tell us how much total matter exists. Lensing tells us how it's arranged. Together, they peel back layers of cosmic history, showing how dark matter's gravity sculpted the universe from a smooth primordial soup into the intricate tapestry we see today. Perhaps the most profound insight comes from anomalies. Some regions of the CMB appear lensed more strongly than expected, hinting at dark matter clumps with no visible galaxies, ghostly halos lurking in the darkness. Others suggest dark matter might interact with itself in ways we don't yet understand, leaving faint fingerprints in the lensing patterns. These aren't just curiosities, they're clues to the nature of 85% of the universe's matter, a substance so mysterious we only know it by the shadows it casts. So while the CMB's light began as a flash from the Big Bang, its journey transformed it into something even more valuable, a cosmic X-ray revealing the invisible bones of the universe. Every distortion, every subtle warp is a message from the dark side of reality, and we're only just beginning to decode it. The cosmic microwave background is the universe's oldest light, but it won't last forever. Over timescales that dwarf the current age of the cosmos, this ancient glow will fade from a whisper into silence, erased by the relentless expansion of space itself. Imagine a campfire burning low in an endless desert. At first, its warmth is unmistakable, but as the night stretches on and the desert grows, the embers cool, the glow dims, until finally, nothing remains but darkness and cold. That's the fate awaiting the CMB, not in billions of years, but trillions. Right now, the CMB is detectable because its microwaves fall within a range our telescopes can capture, just a few degrees above absolute zero. But as the universe accelerates outward, driven by dark energy's mysterious push, those wavelengths will stretch further, redshifting into longer and weaker radio waves. In roughly 150 billion years, the CMB's temperature will have dropped so low below 1/1000th of a Kelvin that its signal will blend into the ambient noise of the cosmos. The photons will still exist, but their energy will be diluted beyond recognition, like a single drop of ink stirred into an ocean. The implications are staggering. For any civilization arising in that distant epoch, the afterglow of the Big Bang will be invisible, lost in the cosmic static. Without the CMB as a reference, piecing together the universe's origins would be nearly impossible. No relic radiation means no smoking gun for the Big Bang, no primordial snapshot of the cosmos's infancy. Astronomers of the far future might never know the universe had a fiery beginning at all. They could gaze into the void and see only endless expansion, wondering if everything had simply always been cold, dark, and empty. But the CMB's disappearance isn't just about lost knowledge, it's about cosmic loneliness. As the universe expands, galaxies beyond our local group will redshift out of view, their light stretched beyond detectability. The night sky, now teeming with distant stars, will grow barren. The CMB's fade out is merely the first act in this grand isolation, a preview of a future where the universe's history becomes unknowable. Even if intelligence persists for trillions of years, the evidence of its own origins will have vanished like footprints washed away by an infinite tide. Yet there's a strange beauty in this erasure. The CMB's gradual dissolution mirrors the universe's own trajectory from a hot, dense beginning to an ever-cooling, ever-darkening expanse. It's a reminder that the cosmos isn't static. It's a story with chapters that unfold across epochs we can scarcely fathom. And while the CMB will one day vanish, its legacy is indelible. The galaxies, stars, and planets that formed from its subtle wrinkles are its enduring testament, scattered like ashes from a fire that once lit the whole sky. So while we still can, we listen. Every measurement, every map of the CMB is a snapshot of a signal that won't last forever. It's the universe's oldest broadcast, and one day its transmission will end. But for now, the afterglow remains a flickering candle in the dark, holding secrets we're only beginning to understand. From the faintest whisper of microwaves to the grandest maps of cosmic structure, the cosmic microwave background isn't just a relic, it's the cornerstone of modern cosmology. Every ripple in its glow, every subtle distortion in its light, tells a story that stretches back to the very first moments of existence. It's the universe's own origin story, written in photons that have traveled for over 13 billion years to reach us. Through 30 astonishing revelations, we've seen how this ancient light confirms the Big Bang, weighs invisible dark matter, and even hints at realities beyond our own. It's more than radiation, it's a time machine, a blueprint, and a detective all in one. But here's the most thrilling part: the CMB isn't done talking. With every new telescope, every sharper map, we uncover deeper layers of its secrets. Future missions might finally catch the whispers of primordial gravitational waves in its polarization, or stumble upon anomalies that rewrite our understanding of inflation. Could the cold spot be proof of a parallel universe? Do those large-scale asymmetries hint at dimensions we can't yet see? The CMB is a puzzle with pieces we're still learning to fit together, and the next breakthrough could be just one observation away. So as we stand here, bathed in the afterglow of creation, let's ask one final question. What do you think the CMB will reveal next? Will it expose the true nature of dark energy, or unveil relics from before the Big Bang itself? The universe is still speaking, and its oldest light has so much left to say. If you've enjoyed this journey through the cosmos's greatest mystery, make sure to subscribe, because the next discovery could rewrite everything we know. The CMB has been our guide this far. Where will it take